Good morning, students. Chapter 6, Electromagnetic Induction. Yes, we have completed Faraday's 3 experiments. Conclusion, Faraday's law, Lenz's law, then what is magnetic flux, what is motional EMF, and their cases. Okay, now we will see one important topic of this chapter, that is eddy current. What is eddy current? Okay, yes, throughout this chapter you have to remember only one concept, that is due to change in magnetic flux, due to change in magnetic flux linked with circuit or body or object, linked with circuit, EMF is induced. So yes, we can say current is generated. Current is generated. With the help of Faraday's law, we can find what is magnitude of EMF and current. With the help of Lenz's law, we can find direction of EMF and current. Yes. What is eddy current? What is eddy current? Yes, due to change in magnetic flux linked with circuit. If we take conductors, okay, if we have metal objects, metal bodies, okay, some appliances made up of metal, if they are under the influence of changing magnetic flux, if we have metal objects, metal bodies, metal appliances, and they are under the influence of changing magnetic flux, then yes, currents are produced in such metals. When conductors, metals, okay, they are under influence of changing magnetic flux, then yes, due to change in magnetic flux, EMF is induced, current is produced. So yes, when conductors or metals, they are under influence of changing magnetic flux, currents produced are like, they are similar to currents produced are like swirling eddies in water. Swirling eddies in water, like this. Okay, they are circulatory in nature. They are circular currents. Clear about this? So yes, when conductors or matter, they are under the influence of changing magnetic flux, EMF is induced, currents are produced, and they are like swirling eddies in water. Means they are circulatory in nature. And that's why such current is called eddy current. Such current is called eddy current because it is circular current. Clear about this? So yes, this eddy current is nothing but the same concept. Due to change in magnetic flux, current is induced, but these currents are circulatory in nature. They are circulatory in nature. That's why they are called eddy currents. Clear about this? So yes, eddy currents. Now, what is meaning of this eddy current that we have discussed? Now, is eddy current producing conductor, they have advantages or disadvantages? Yes, both. Okay, first of all, we will discuss about disadvantages. What happens? See, whenever from conductor current passes, it also has some resistance. Yes or no? So in conductor, according to is I square RT. Is I square RT. Yes or no? In conductor, if current flowing is I, resistance is R, then according to Joule's law, heat energy produced H is equal to is I square RT. And this heat energy is dissipating in form of heat. In form of heat. So we can say okay, this much amount of energy is wasted. This much amount of energy is wasted. Clear about this? So yes, whenever eddy currents are produced in metals, in conductors, this current will produce this much amount of energy which is dissipated in form of heat. Means it is nothing but loss. It is loss of energy. It is loss of energy. So how to reduce this effect? Yes, we have to decrease I, that is eddy current. That is eddy current. We have to minimize effect of eddy current. We have to minimize effect of eddy current. If we decrease I according to I square RT, this energy dissipating in form of heat decreases. Clear about this? So yes, how to decrease now eddy current? So we will take one example, and it is also one theory which is called electromagnetic damping. Electromagnetic damping. What is electromagnetic damping? See, if I have two strong magnetic poles like this, okay, between these two magnetic poles there is one plate, which is oscillating, between these two magnetic poles there is one plate made up of conductor, is oscillating. Clear about this? As these are two poles, that is North Pole and it is South Pole. Okay, so yes, magnetic field, it is only in this region. Yes or no? So if this metallic plate oscillates in this region, see, magnetic field is only in this region. In this region, no magnetic field. Here magnetic field is equal to 0. This side also magnetic field is equal to 0. Magnetic field is only in this region. So what happens? See, whenever this metallic plate, okay, when this metallic plate is oscillating like this, see, here magnetic field is 0. So magnetic flux linked with metallic plate is 0. Now it is in this region. Magnetic field not 0. Magnetic flux not 0. Here there is some flux linked with this plate. So see, due to change in magnetic field, there is change in magnetic flux. Yes or no? Yes. In this region, no magnetic field. In this region, there is magnetic field. So when this plate is oscillating, we can say plate is oscillating in varying magnetic field. 0 magnetic field, non-zero magnetic field, 0 magnetic field. Again, 0 magnetic field, non-zero magnetic field, 0 magnetic field. So due to change in magnetic field, there is change in magnetic flux. EMF E is induced, and eddy current I is induced. Clear about this? And according to Lenz's law, we know that these eddy currents are induced such that they opposes their cause. What is cause? Oscillations. So in this plate, EMF is induced, eddy current I is induced such that it opposes oscillations of plate. It opposes oscillations of plate. So here I have to write according to Lenz's law. According to Lenz's law. According to Lenz's law. Such eddy currents opposes cause means oscillations, because due to oscillations EMF is induced. Due to oscillation, there is change in magnetic field, there is change in flux, EMF is induced, eddy current is induced. So what is the reason eddy current is induced? Oscillations. What is reason? Oscillation. Okay. Oscillations. Clear about this? So yes, according to Lenz's law, such eddy currents opposes cause. That is oscillations. That is oscillations. Clear about this? So yes, as it opposes oscillations, means these oscillations, they will decrease, they will decrease, they will decrease, and after some time it will stop oscillating. It will stop oscillating. Clear about this? So oscillations are damped. Oscillations of plate is damped. Okay, and therefore it is called electromagnetic damping. It is called electromagnetic damping. Clear about this? Oscillations of plate is damped. Oscillations of plate is damped, and therefore it is called electromagnetic damping. Now, how to reduce this damping? How to reduce damping? How to reduce damping? Yes, to reduce damping, you have to reduce eddy current. You have to reduce eddy current. And how to reduce eddy current? See, here we have used a plate like this, fully made up of metal like this. To reduce effect of eddy current, we have to make plate like this, with holes, okay, or slotted. Slotted means like this. Slotted is like this. Clear about this? It is plate. It is completely made up of metal. Okay. To minimize effect of eddy current, we have to make plate. Having holes inside it, or slotted. So what happens when we make holes or it is slotted? Effective area decreases. Area decreases, then what happens? Yes, current means what? Current means flow of charges. Here, in these two cases, as area decreases, effective area decreases, so the region to flow charge decreases. For electron to move, now there are not too large area. Okay, area decreases. So yes, flow of charges, now they are restricted. Flow of charges are restricted. Clear about this? So yes, as area increases, only in some area electron will move. Okay, so yes, eddy current decreases, and eddy current decreases means oppose decreases. And oppose decreases, it means this plate will continue to oscillate. Clear about this? So what is electromagnetic damping? See, in this region there is magnetic field, in this region no magnetic field. Due to oscillations of plate, there is changing magnetic field, there is changing magnetic flux linked with this plate, EMF is induced, eddy current I is induced. According to Lenz's law, eddy currents opposes their cause, means oscillations. So oscillations are damped. Oscillations are damped. That's why it is called electromagnetic damping. How to reduce this damping or how to reduce eddy current? To reduce eddy current, you have to decrease effective area. How to decrease effective area? With holes, or this plate is made slotted. This plate is made slotted. Clear about this? So yes, it is one question, which is what is electromagnetic damping and how to reduce it. One another application, okay, in transformer, in dynamo, in motor, okay, some metallic core is used. Some metallic core is used, and on metallic core, okay, suppose it is one piece. On that piece, wire is wound. On that piece, wire is wound, and from wire, current is passing. So due to current, magnetic field is produced. Due to magnetic field, there is change in flux. Due to change in flux, eddy currents are produced. Eddy currents are produced. And due to eddy current, according to I square R T, Joule head produces and it is dissipated in form of heat. Means energy is wasted. Energy is wasted. So without using a single piece of core like this, slotted core is used. Slotted core or laminated core. Laminated core means what? Laminated core means what? See here, it is conductor. Okay, then insulating medium. Then again conductor, then again insulating medium, then again conductor, then again insulating medium. Okay, conductor, then insulating medium. Then what happens? See, this object is fully made up of conductor. Means electron can flow anywhere from this point to this point, this point to this point, this point to this point, this point to this point. Because here effective area is more. Effective area is more. So eddy currents produced are also more. But in this case, what happens? Okay, between these two region of conductor, there is insulating medium. So any charge cannot move from this one part to another part due to this insulating medium. So again, effective area decreases, eddy current decreases, and if eddy current decreases, I square RT, that is loss of energy decreases. So yes, in motors, in dynamos, whenever core is used, that core is laminated. One conducting plate, insulating medium. Conducting plate, insulating medium. Conducting plate, insulating medium. Means each and every layer, they are insulated from each other. So charge from one plate cannot move to another plate. Means effective area decreases, eddy current decreases, loss of heat also decreases. Clear about this? So yes, what is eddy current? What is electromagnetic damping? Okay, and how to minimize it. Now, these are disadvantages. We have to decrease eddy current in such cases. But yes, eddy current, this concept, it is also used. Means it has some advantages. In some applications, eddy current is used. So what are applications of eddy current? We will see. Now we will see applications of eddy currents. See, first, magnetic braking in trains. What happens in this situation? See, yes, strong magnets are used. Due to that magnets, magnetic field is produced, magnetic flux is produced. Due to change in magnetic field, due to change in magnetic flux, EMF is induced, current is induced, and this current is induced such that it opposes motion of train. Yes, whenever we have to apply brake, these magnets are activated. Due to activation of magnets, there is change in magnetic field, there is change in magnetic flux, EMF is induced, current is induced, which opposes motion of train. Magnetic braking in trains. Clear about this? Second, Electromagnetic damping. What is electromagnetic damping? Damping means again. It decreases its oscillation. Okay. Yes. Again, in some meter, for example, galvanometer. We know that in galvanometer, pointer moves from 0 towards any value. Yes or no? Yes. So, electromagnetic damping means what? Whenever magnet placed in a galvanometer is activated, due to that magnetic field produces, flux produces, EMF induces, current produces, and that current produces such that it brings coil in its normal position, on its normal position. So yes, it is called electromagnetic damping. Third one is induction furnace. You know that why? What is purpose of furnace? Furnace that is used to melt any metals, to make alloys. Yes or no? Furnace is used to melt any metals. How? Like this. Okay. If it is a metal piece, wire is wound, alternating current is passed from this. Why alternating current? Because alternating current means value of I changes. Due to that, magnetic field changes. Due to that, flux changes with this metal. Due to that, EMF is induced, and due to that, eddy currents are produced. And if eddy currents are produced in metal, this eddy current is produced in metal. Okay, and due to that, I square RT, joule heat is produced, and due to that joule heat, that metal melts. Clear about this? So yes, it is induction furnace. Clear about this? Last one is electric power meters. Again, what is electric power meters? In electric power meters, magnets are placed. When that magnets are activated, due to change in magnetic field, there is change in magnetic flux, EMF is induced, current is produced, and now current is produced in such a direction that it will rotate indicator. Clear about this? So it is use of eddy currents. It is uses of eddy currents. Okay. So yes, you have to write these 4 applications of eddy currents from textbook in detail. Yes, what is eddy current? What is electromagnetic damping? Applications of eddy current you have to write from textbook. It is in shorthand. Clear about this? So yes, it is all about eddy current. Okay, now we will see some questions. See, example 6.2. Example 6.2. What is example 6.2? Here it is. A square loop having side 10 centimeter and resistance 0.5 ohm is placed in vertical plane such that it is in east-west plane. Magnetic field, uniform magnetic field 0.10 Tesla is in north-south direction. Magnetic field is decreased to 0 in 0.70 second. At a steady rate, you have to find what is magnitude of induced EMF and what is current. See, you are given a square loop. Okay, having side 10 centimeters. So yes, how to write data? Yes, we will write data. 10 is equal to 10 centimeter. So area A is equal to it is L square. Simple. Area A is equal to it is L square. Yes. Magnetic field. EMF, induced EMF means, see, how to find induced EMF. E is equal to, mode of E is equal to delta phi upon delta T. Delta phi means this phi 2 minus phi 1 upon, here it is delta. So first of all we have to find phi 2, then we have to find phi 2, and then we have to apply delta T. Simple? Okay. So first of all we will find phi 1. Phi 1 is equal to, how to find phi 1? Square loop, side 10 centimeter, resistance 0.5 ohm is placed in vertical plane east-west. Vertical plane like this. Plane is placed like this in east-west direction. Clear about this? Okay. Yes, in east-west. Magnetic field. Here it is. Magnetic field. It is 0.1 Tesla. 0.1 Tesla. what is equation of flux? Equation of flux is phi is equal to AB cos theta. So here it is A B1 cos theta. What is theta? That is angle between area and magnetic field. See, this square loop is placed in vertical plane in east-west plane like this. Like this. Okay, so its area vector is normal to its area vector is normal to its area vector is normal to it. Also, magnetic field B, it is in north-south direction. North-south direction is again in this direction. Clear about this? Again in this direction. Yes or no? You have to understand data. You have to understand data. Okay. This square plate is placed like this in east-west plane. So its area vector is normal to its area vector is normal to it, and magnetic field is also from north to south. So yes, they are in the same direction. So angle theta will be 0. Angle theta will be 0. So yes, here it is only A B1. Here it is only A B1, and yes, it is value of B1. B1 is equal to 0.10 Tesla. So it is L square B1. Now, how to find final flux phi? Final flux phi 2. B decreases to 0. B decreases to 0. So here it is A B2 cos theta. Here it is A 0. Because it reduces to 0. Means second magnetic field B2 is equal to 0. Is equal to 0. So yes, phi 2 becomes 0. Phi 2 becomes 0. Clear about this? Clear about this? As we have to find magnitude of EMF, here we have to take its magnitude. Here we have to take its magnitude. So now it is simple. We have to find mode E. Mode E is equal to, it is phi 2. What is phi 2? 0 minus phi 1 divided by delta T. So it is only phi 1 upon delta T. Phi 1 L is given, B1 is given. You can easily find what is value of induced EMF. Okay, and then you have to find I. I is equal to, it is mode E upon R. What is R? Resistance. R is given. Resistance R is given. It is 0.5. It is 0.5. Clear about this? So yes, it is again one simple question. One simple question. Okay. Example 6.3. A circular coil having radius R is equal to 10 cm, numbers of turns 500, R is equal to 2 ohm, is plane is perpendicular to BH. Its plane is perpendicular to BH, which is like this. See, it is plane perpendicular to BH. Area vector is also perpendicular. So here we can say that angle between A and B, like this. See, it is circular coil. Magnetic field is perpendicular to B. Magnetic field is perpendicular to A, and area vector is also perpendicular to A. So here initial angle theta is 0. Initial angle theta is 0 because plane is perpendicular to magnetic field. So then it is rotated by angle 180 degree in 0.25 second. Estimate what is mode of EI when T is equal to 3 to 10 to minus 5 Tesla. Again we have to use this same equation. That is mode E is equal to delta phi upon delta T is equal to phi 2 minus phi 1 upon delta T. First of all, we will find phi 1, initial flux. Phi 1 is equal to, it is A BH cos 0, because initially this plane is perpendicular to BH, means they are in same direction. Area and magnetic field, area vector and magnetic field, they are in same direction. So yes, here it is A BH. Where what is A? A is equal to, it is pi r square. But phi, here you have to consider these numbers of turns. So yes, we can write this number of turns later. Okay. What is phi 2? Phi 2 is equal to, it is phi 2 is equal to, it is, okay, it is A BH cos 180. Why cos 180? Because that coil is rotated by 180 degrees. So here cos 180 is minus 1. So it is minus A BH. So here it is minus A BH. Clear about this? Now what is the equation of induced EMF? Mode E is equal to N delta phi upon delta T. Delta phi upon delta T is equal to N. Delta phi upon delta T means it is phi 2 minus phi 1 upon delta T is equal to N. Delta phi upon delta T. Phi 2 is minus A BH. minus ABH upon delta T. So mode of E is equal to, here it is 2 NaBH divided by delta T. You are given 2, you are given Na is pi r square, and you are also given BH. You have to find what is value of this mode E. Then I is equal to this mode E upon R, where R, that is resistance of coil, it is also given. It is also given. Clear? So yes, here it is. What is EMF induced in coil and what is current induced in coil? In this question, there is change in magnetic flux due to change in magnetic field. Initially magnetic field is this, then magnetic field is 0. In this case, area is constant, magnetic field is constant, just orientation between B and A changes, means angle changes. And due to change in angle, there is change in flux. Clear about this? Concept is same. Due to change in magnetic flux, EMF is induced, current is produced. But change in magnetic flux, here it is due to change in magnetic field, here it is due to change in angle. Clear about this? So yes, these are some questions which are easy based on Faraday's law. Okay? So yes students, in this lecture we have discussed about eddy current and 2 questions. You have to calculate these questions and write your answer in comment box. Okay? This is it for today.